Okay, so today I'm going to go through the concept of depth first search. Um, the focus will be how to actually ensure you've gone through all of the nodes. So for purposes of illustration, I'm going to use the simplest type of graph, just like a binary tree. And then the problem statement is going to be finding the minimum value inside that binary tree. So a binary tree is something that always has two roots like that, or two nodes like that. And that's what I mean by a binary tree. So because of the twos, that's how it looks like. So might want to look at might want to think through the values that are going to be there. So for the purposes of this, maybe let me start with 2, 3, 7, you know. Then this will also have children of its own. So maybe it will be 8, 9, maybe 1, 5. So it kind of doesn't matter the values that are there. The point is I wanted to illustrate how the graph looks like. Now, once you have a good sense of this graph, the question is how would I find the minimum value. So how you'd go about that is what now called the depth first search. So in effect, what you want to do is we'll just go ahead and copy this item. So what you want to do is basically go depth first. That means we start on this side. So if you're starting on this side, we'll go through that tree that has two options. We still continue going until we find that. Then we go a bit one step. We go one step back. Then we get this number 9. Then we go one step back, and then we finally go back. So we do that for everything that's on the left side. Then for everything that's on the right, kind of a similar case. So we put 7. There's only one option there. And then we get what's on the 5. Then we go back. Then we get on this side what's on the 1. Then we go back. So what I want you to notice here is, if for one reason or another all of this disappeared, then we'll have a similar problem, but it will be a smaller problem. In a similar way, if all this disappeared, then we'd have a similar problem, but with only one node. So what that tells us is that this is a good place to use recursion. So how would we use recursion in this case? Well, the first thing to think about is because recursion usually has two parts: the base case plus the recursive case. So then what's the base case? The base case is when we are here and there are no further children. The recursive case is where you have both a left and a right. So this tells us something. We need at least 3 trackers. The first tracker would be the current smallest value, because we always need to keep track of the smallest value. Then the next thing that we need to keep track at is what's from the left, what's the smallest, from the right, what is the smallest. Of course, these two only make sense in the recursive case. And then also want to get a situation if the node that you have been given is completely empty, then how do we deal with that? Because the problem here is the smallest value, then we can assume that we're just going to give infinite, which is the largest possible number. Okay, so now the question is, we are now here, so we have our nodes. We have already decided what are our main variables. The question is, what do we check it against? So we start by assuming the current node is the smallest. Then we check, we get the smallest value that comes from the left stream. So we don't know what that's gonna be, but we know there's gonna be a left smallest coming from there. We also know that there is going to be a right smallest coming from here. We don't know what that is yet, but at this point in time, we can go ahead and make a comparison and say that, because remember we said we'll start with this side. So then we'd say the smallest value is going to be between what is the current, so what we have at this point in time, the smallest is going to be a minimum of that. So the mean, let's do this. It's going to be the minimum value of what's currently the smallest and what comes left as the smallest. And just like that, we have the smallest from that side. And then again, we want to compare with what is coming from the right. So it's the smallest is equals to the minimum of, again, this smallest and what's coming from the right, the smallest. Now, the question then is, how do we find what this left smallest is and what this right smallest is? So we need to implement a function called find smallest, and that's how we get this value. So I'd have the depth. Let me actually do this here. You'd have to call a find smallest that takes in some kind of graph, right? That's how you get this value. So then I'd say left smallest. Okay, at this point in time, I'm just going to put this in its own page so it's easy to understand. Okay, so the next thing I want to get is left smallest, which I'm actually going to equate. Left smallest, I'm going to equate to this number, to a new function that is not yet defined, which will be like find smallest, and it will just takes a node. Now this is where you realize that everything that sits inside here actually sits within a larger structure. Remember, we talked, said you're going to use recursion. So the right smallest is going to kind of come here. So the right smallest, again, we do find smallest, but now we pass it the right node, right? So on this one, the other side, we pass it the left node. This side we pass it the left node. Okay, so we pass it both the right. Okay, that's clear. That way you get the left smallest and you get the right smallest. Now the question is, where did this smallest first come from? And this comes from the current value. We assume it's the least value when we start. So we say, whenever we start, we say smallest is equals to the smallest value that we have. We assume it's the current, because remember, that's how we kind of came into this. Actually, instead of calling it root, because we might not be at root, probably at node, it's going to call it node.val. All right, so then we are currently at that stage. So what do we do now? First of all, we want to actually, because remember, this assumes that this node has a value, it might actually be none. So we want to check that situation. So if node is none, actually I think I can, if node is none, then there's no point in continuing the rest of this code, and I can just return that infinity, right? That didn't work, so I'll just return float infinity. That's how you define infinity in Python, right? So now you're in a good place. Now the question is, how do you find the smallest? Well, this is how you find the smallest. You define it at this stage. So you find the smallest, and then to it you pass in, obviously it always takes the self, and then you pass in the node. Right, so obviously this code will not compile, but I'm hoping the concept makes sense. We always start with checking if there's no value, and that's out. The next thing, that means that whatever you've been given is actually empty, and you can return the infinite value. Then the next thing is you start checking. You assume the current node is the smallest, then you go to find left on the, so you basically want to find the smallest on its left here. For now you can just assume that this tree ends here, so you try find the left on that side. You get the smallest value, you compare with it. Is it the smallest? Then you go to the right again, find the smallest value on everything that is there, and then come here and then compare, and now you have what in effect is the smallest value. Of course, if you got here at this point in time, they would, if you got here, because remember this has children, what the algorithm is checking is basically we have come to this stage. Again, we assume the current node is the smallest, and then we check is there anything that is smaller downstream, starting again to the left and again to the right. If this is the root node, then we return this value and say, okay, this is the smallest. However, if it comes here and it's checked again is this current value and the left node, then what is actually passed up is the smallest of these three. And that's how that algorithm will work. Yeah, let me know if my explanation was clear, or if there's anything I could have done to explain it a bit better. I'll try to also put in code that compiles in a later video. Thank you.